Thank you very much. I'm glad to have this opportunity to give a presentation on our project related to the control of the physical properties of the ferroelectric domain walls, specifically the electrical conductance. So that's the main topic of my presentation, and specifically I will be discussing how this conductance can be controlled in the ferroelectric lithium niobate thin film. So this project has been carried out in collaboration with several groups from Penn State, University of Limerick in Ireland, and Queen's University in Belfast in UK. So I will consider two main aspects in this presentation. So first, domain wall conductance, so how it could be tuned, and second, how it can be used in application for working electronic devices, specifically domain wall-based membristors. So appearance of the domain walls in ferroelectric materials is a result of splitting of the volume of the material into domains, which are energetically equivalent regions with macro nanoscopic dimensions. So they have different polarization. And this is kind of a mechanism that minimizes the free energy of the system. So these domains are separated by the domain boundaries, and historically these entities, they were overlooked, so they were considered like minor entities of minor importance, and therefore properties were not investigated. So basically they were dismissed until recently, when the advent of high resolution electron microscopy and local probe microscopy techniques, as well as progress in first principle modeling, so made it abundantly clear that the domain walls actually possess their own physical properties, so very different structure, symmetry, and therefore they possess a set of very diverse functional characteristics that are completely different from those of the domains that they delineate. So for example, these domain walls can be metallic or even potentially superconducting, while the domains that they separate are insulating. And recent research even shows that domain walls can represent a completely new phase, so with distinct chemistry and magnetic behavior. So these observations of quite unusual physical properties of the ferroelectric domain walls have been coupled with progressive realization that there could be enormous potential in application of these entities in the real physical devices. And just to kind of borrow this expression from my colleague, Gustavo Catalan, the wall is a device. And so he kind of coined this phrase almost 10 years ago, and there was enormous developments since then. So the key feature of the domain walls is that they are two-dimensional functional objects, and they can be created, erased, or controllably moved from one point to another using precise positioning methods by applying external electric or mechanical elastic fields. So their transport properties can be tuned by electrical or mechanical or chemical means. And just to emphasize that they are dynamic entities that can be deployed and manipulated to change their position so that we can use them in order to develop circuits. The properties, the structure of these circuits could be changed within the existing device, and therefore it could be used in order to control and modulate the device functional properties. So this rapidly evolving field has been termed as domain wall nanoelectronics. And just to give you a brief example of this new type of devices based on the domain walls, so it's shown here. So the function of these devices is entirely related to the presence or absence of the domain walls. For example, if you have electrically conducting walls. So electric field induced switching between structures where the main walls connect the electrodes, like here, or where the main walls is absent and the four electrodes are disconnected, could give rise to low or high resistance states of the devices. So equally, the number of the conducting domain walls connecting these electrodes could be changed in a controlled manner by varying the amplitude of the applied bias. And therefore, we can create a series of distinct resistance states, making a tunable memristive devices. So in other words, conducting domain walls in ferroelectrics can act as two-dimensional sheet conductors with a wide range of functional properties. And in addition, so they have kind of this unique property of being agile. So they can be moved, they can be injected, they could be annihilated. So giving rise to kind of very new forms of dynamic electronic devices. However, it's necessary to emphasize that in order to make use of these domain wall properties as active elements in nanoelectronic circuits and devices, so we need to have the ability to efficiently control the charge transport in the walls themselves. So this is absolutely essential for the device application. And it has been shown already that domain wall conductivity is not a fixed property. So it's actually transient. And the conducting state is not retained, for example, when the bias is turned off. So the reversible switching from resistive to conductive behavior of the charged domain walls in erbium manganite was attributed to the formation or activation of the inversion layer, acting as the channel for the charge transport. So the potential advantage of this effect is unfortunately offset by the difficulty in manipulating of the domain structure. So this limits the writing process, which is desirable for the programmable devices. So if you then move to lithium niobate, so it's a classic ferroelectric material, so it's a unique material with trigonal symmetry, where polarization aligns along the threefold z-axis, so which gives rise only to two types of domains, antiparallel domains. And early theoretical and experimental studies have shown that the 180-degree domain walls that separate antiparallel domains, so that they could be created by electrical pooling. So they could be slightly inclined with respect to the polar axis, indicating that these domain walls are not neutral, but they could carry positive or negative charges due to the head-to-head or tail-to-tail domain alignment. So several reports gave ample evidence that only head-to-head domain walls are actually conducting. This has been kind of demonstrated by the means of scanning probe microscopy technique, conducting AFM. You can see this bright line that corresponds to the higher conducting regions coinciding with the position of the domain walls. And it has been shown that the inclination angle can be increased by an applied voltage, leading to the domain wall conductivity that could be enhanced by several orders of magnitude. So here you can see that the larger the angle between the domain wall and the polar axis, so then the conductance will be changing. And it's true only for the head-to-head domain wall, while the tail-to-tail domain walls are actually insulated. So our studies actually follow up of this initial finding. And in our project, we used the ultra-thin crystals or thin films of Z-cut lithium niobate, which were prepared by the iron sliced method on the platinized substrate. So in the as-prepared film, the polarization points away from the bottom electrode, and it's typically the single domain state. So there are no domains and no domain walls. So generally, bulk lithium niobate is of the congruent composition, and it has relatively high coercive field, which means that the sample could be difficult to switch, but if you reduce the thickness, though, then the voltage that could be used to switch polarization would be within the kind of range that is affordable when you operate it in scanning probe microscopy. So we just did first preliminary testing of the switching of the polarization in these films of lithium niobate using scanning probe microscopy techniques. So the resulting domains that are shown here that have been visualized by means of piezo response force microscopy. It's a well-known method for delineation of the domains in ferroelectric materials based on the piezoelectric effect. And the corresponding conducting FM image shows that indeed here we have conducting domain walls, where conductivity depends on the wall orientation and also geometry of the resulting domains. So you can see that this hysteresis loop indicates that there is asymmetry in the switch local coercive voltages, so it's more easy to switch into the downward polarization than in the upward. So this slide shows a periodical domain pattern that we produced by scanning probe microscopy. So we scanned the surface with the electrically biased tip, and then we visualized it in PFM, tested the conductivity of the domain walls using conducting FM. In addition to that, we performed cross-sectional examination of the produced pattern when we looked in the direction parallel to the surface, shown here. And we see that this scanning transmission electron microscopy revealed strongly inclined head-to-head domain walls. So with a typical inclination angle as large as 20 degrees. And these domain walls indeed show high conductivity in agreement with the previous reports. To check the theoretical prediction that the conductivity is proportional to the degree of inclination, in other words, that the highest conductance would be achieved at the head-to-head domain walls that are perpendicular to the polar axis. So we created these structures in the X-cut lithium niobate samples, and in this case, we found that the current level is an order of magnitude lower here than here. So this is, we have kind of a perpendicular domain wall. Here we have just inclined domain walls. Nevertheless, they show much higher conductivity. So it's probably purely kind of technical kind of problem, because in this case, the domain wall just doesn't reach from the upper surface to the bottom electrodes. So in other words, there is no conducting channel. So, and therefore, whatever we measure here doesn't represent the true electric conductivity of this domain wall. So, however, the most significant feature that we observed for these head-to-head domain walls is that their conductivity could be continuously tuned by application of the external bias that we refer to as a set bias. So we investigated this effect in a following way. First, we produced a single domain wall by creating by domain pattern. So here you can see PFM image shows anti-parallel domain walls with polarization either in or out of the plane. And here is the image of the domain boundary, and corresponding conducting FM image show that it is indeed conducting. And then we scan this area containing this written domain wall with the tip under a subcoercive DC bias. So we call it subcoercive bias as a set bias. So we didn't change the polarization as we confirmed by PFM. So the next step was to check the tunability, the change in the domain wall conductance using conducting FM. So you can see that after we scanned this domain wall with a low negative bias, so we could completely erase conductivity of the domain wall, we turn it into the insulating state. So then if you scan it with the kind of successively increase in positive bias, so we can recover this conductivity, so it becomes highly conducting. And this process is repeatable, so it's reversible, so we can erase conductivity again, and then we can kind of recreate it back. So it showed that the conductivity of the domain walls is tunable. It could be also controlled locally at the level of below 100 nanometer in size by application of the local set bias. And these plots just show that domain wall conductivity is a function of the set voltage. And you can see that it follows this hysteretic behavior. So low conductivity can be created by small negative bias, while we can reach much higher conductance if you apply small subcoercive positive bias. So clear effect of electrically tunable domain wall conductivity. So local IV spectroscopy of these domain walls has been carried out in order to get additional insight into the memoristic behavior. So we have typical counterclockwise hysteresis in the positive half cycle and clockwise hysteresis in the negative half cycle, due to the fact that the positive voltage enhances the domain wall conductivity while negative bias suppresses it. And on the left, you can see these consecutive IV cycles within this voltage range that incorporates positive and negative voltages, and that from cycle to cycle, conductivity of the domain wall is changing, which is an indication that it can depends on the prehistory of what was done to the domain wall before the conductivity has been tested. So it's a clear manifestation of memoristic behavior in these objects. So for the sake of time, I would like to skip this kind of detailed explanation here. I just would like to draw attention to the fact that conductivity of relatively small domains here, so approximately less than 100 nanometers in size, is much higher than the conductivity of the domain walls delineating much larger domain. So we will see why it's relevant to this presentation later. So, so the results that we obtained seems to be consistent with the earlier reports that, for example, in the PZT ferroelectric films, another archetype ferroelectric material. So the most conducting entity were the nanoscale domains. So where the macroscopic domains didn't show any conductivity. So here you can see that there is also hysteresis behavior measured on the in the films with nanoscale domains. And it was suggested that this conductance should be due to the bulk domain, not domain wall, but domain conductivity. Assuming that there is direct tunneling effect, they used relatively thin films, as well as due to the formation of the metallic conduction path immediately adjacent to the domain walls. So like they shown here. And with respect to our results, so I think we can exclude the tunneling effect because of the thickness of our films of approximately 500 nanometers. But the second effect can certainly play a role. So nanodomains represent single nucleus of opposite polarization, and within kind of in general should be decorated by the curved domain walls. So domain walls should be inclined, and this should lead to the local modification of the carrier density due to the accumulation of a compensating or screening charge in order to kind of compensate the bound polarization charge. So therefore, assuming that the conducting behavior of the head-to-head domain walls in our films of lithium nanobate as a result of polarization charge discontinuity at the inclined domain walls. So we can speculate that application of the set voltage or subcoercive voltage that modulates the domain wall conductance would change the accumulated charge density. And that's why we can kind of tune the domain wall conductivity. So the range of conductance changed by the set voltage that we use is much larger in comparison with the domain wall conductance that was observed after polarization reversal. So that's kind of important issue to keep in mind. And just to give you an idea, so that the difference between the conductivity that we can create by applying the set voltage and conductivity of the domain wall right after we create the domain walls could be up to 1 order of magnitude. So which means that there should be probably additional mechanism that kind of is responsible for the electrically tunable domain wall conductance. So in order to get insight into this mechanism, we had a more careful look at the domain structure. So here we have PFM image of the domain walls after application of positive and another positive set bias with corresponding conducting FM image of the domain walls. So as you can see, this set bias doesn't change the domain structure. However, so detailed examination of the PFM after we apply negative set bias shows that actually there is a very small, tiny shift of the domain wall by a distance of in the order of 10 to 20 nanometers. And this shift is accompanied by the complete disappearance of the domain wall conductance. So it was conducting and it became insulated. So what's going on? So next slide show that actually gives a little bit more information to this. Again, individual domain wall that has been created by high voltage, and then it was scanned by very subcoercive set bias of negative polarity. So, and then we can change the conductivity and the local level that I mentioned at the beginning. So we can create part of the domain wall conducting while the rest would be insulated. So the most important part here is that cross-sectional STM studies reveal not simply an inclination of the whole domain wall, but it actually shows that domain wall bends at the area very close to the surface. So you see that domain walls is not represented by the straight line on this image, but it actually bends. And that's what we get after we apply negative bias. So in other words, the wall that appears insulating in the conducting FM does show bending of its profile, while conducting walls represented by the straight lines. So this result is consistent with the fact that domain wall conductance decays with time, as is illustrated by the domain conducting FM images taken as a function of time. So you can see that within several hours, so the conductivity of domain walls after we set it in the conducting state would completely decay. And kind of it's similar to the transition to the induced by the negative set voltage, indicated that the mechanism behind the conductance changes is probably due to the relaxation of the charges at this domain wall. So in other words, domain wall with time will kind of spontaneously bend. And this bending is associated with the displacement of the domain wall at its intersection with the upper surface. So we have carried out the phase field simulation of this effect, taking into account the contribution of the free carriers. So we started with this triangular shape domain with inclined domain walls. And then we allowed this structure to relax, and simulation of the domain wall evolution showed that if it's written, if you apply this positive set bias. So then it will spontaneously bend, and the same effect will happen after we apply the negative bias. So in effect, after we wait for some time, this shape of triangular domain will change into this type. And this part of the domain wall, since it doesn't carry any charge due to the polarization discontinuity, so it's electrically neutral domain boundary, so then it doesn't show any conductivity. And so according to this phase field modeling results, the subcoercive voltage controls the domain wall profile, change the bending profile of the domain wall, therefore driving it into the insulating state. If you apply positive bias in contrast, then we will kind of drive it into this shape, and these domain walls are conducting. And this kind of modulation of the domain wall shape actually results in the conductivity by almost 2 orders of magnitude. So indicating that we can have very fine tuning possibility of the domain wall transport properties just by changing the inclination angle. And now very few words about the application of these conducting domain walls for device applications. So basically, since we have conducting domain walls, we can therefore, where we can control the conductance, therefore we can create memristive devices. But there are 2 approaches to this type of device. So we can change the density of the conducting domain walls, because each domain wall would be producing kind of conducting channels. In this case, we'll have to apply high amplitude switching pulses. And another approach is based on the modulation of the domain wall conformation, which could be realized, as you've seen, by small subcoercive voltage. So in these studies, we use graphene as a top electrode in order to have kind of possibility to directly visualize the domain structure after application of the switching pulse or set pulse. And here you can see the first approach demonstration. So initially, when we put graphene on top of lithium niobate film, so everything is a single domain state, and then we applied high voltage pulse, creating polydomain structure. So then we can change the density of domain wall by applying a little bit stronger pulse. Then we can switch the whole volume underneath graphene into the opposite state. So, and you can guess that these structures should have very different conductance, which was also kind of visualized in high magnification PFM images, and corresponding IV curves show that indeed, if we have a single domain state, then we almost have no conductance across this device, but with appearance of high and high density of the domain walls, we have high conductivity. But at some point, the conductance starts to decrease, because at this high voltage, we start to move to the single domain state. So this slide illustrates an alternative approach to resistance modulation based on tuning of the domain wall conductivity, domain walls, rather than kind of creating domain walls. So here we use a subcoercive voltage after we first apply high voltage pulse in order to create polydomain structure. So we drive the device from insulating to the conducting state, as shown by these IV curves. And then we start using subcoercive voltage without changing this polydomain structure. And here you can see this kind of hysteresis loop indicating the dependence of the device conductance upon application of this set pulse. So we can achieve a change of the conductance by almost 2 orders of magnitude without changing the domain structure itself, because this voltage is below the coercive one. So this approach actually allows us to elevate a problem associated with high leakage of the device after it is set in the polydomain state. So if you have highly conducting domain walls, so the switching of polarization in this device becomes difficult. And and it will be kind of also not very beneficial from the viewpoint of power usage. So the approach that we use here, using the subcoercive voltage, kind of in this case provides significant improvement in terms of energy cost or resilience, lifetime, and also controllability of the resistance states. So, and now I got to the end of my presentation. So basically we concluded that the underlying conduction mechanism of the charge domain walls is related to the electron accumulation at the inclined domain walls. And we show that domain wall conductivity can be continuously modulated by subcoercive voltage, because we can change the kind of conformation or shape of these domain walls. These experimental results had been corroborated by the phase field simulation, indicated that indeed, dependent on the alignment or angle between the domain wall and the polar axis, so there is a change in the conductant properties across the length of these domain walls. And at the end, I have to acknowledge the support of the NSF for this project, and I would be glad to take your questions. Thank you.